Okay, so today is all about practicing with our new tests for convergence of infinite series. We have a whole chart with the tests on it. So this is the first page of your packet. Let's scroll up a little bit. The first page of your packet has all the tests, a list of the tests, use it when, how you know the series converges or diverges, and when it tells you nothing. So it's a summary of all the tests here. And then the second page, the back of the first page, is a strategy guide that's like a flow chart. You want to look at each thing in order and decide, does this apply? If not, move to the next test. So what we're going to do in the demo today is to just discuss what tests might be appropriate. We're not going to actually perform the tests. We just want to decide which test we might use. Okay, so this first one, the sum from n equals 0 to infinity of 3 to the n plus 5 over 4 to the n. What I would want you to notice about this one is that you can break it up into two separate series. And then you can rewrite them a little bit to make it clearer which test to use. So we have n equals 0 to infinity of 3 to the n over 4 to the n, plus a separate sum of 5 over 4 to the n. So that works because 3 to the n over 4 to the n plus 5 over 4 to the n have the same denominator, so you would just add them together to get a single fraction. And then you can break it up into two separate sums, just like you can with integrals. Okay, now I'm just going to rewrite these a little bit more. So this is the sum of 3 over 4 all to the n. Because when you raise a fraction to a power, you do the top and the bottom. And then the second one, I'm going to take the 5 right out of the integral, right out of the sum, and I get 1 over 4, and I could raise that whole thing to the n, because 1 to the n is the same thing as just 1. Now, what we should notice, we're going to go through the flow chart for each of these and see what we can come up with for a test for those. Is it a p series? Do we have 1 over n to a number? No, it's 4 to a number, so it's not a p series. Do the terms approach anything other than 0? If you were to write out the terms, do they go to 0? They don't. Let's write out a few and see what we get. So we're starting at n equals 0 on both of these. So when I plug in 0, 3/4 to the 0 is 1. 3/4 to the 1 is 3/4. 3/4 squared is 9/16. 3/4 cubed is 27 over 64. Those terms are getting smaller, right? They're going to 0. Okay, same thing here. If I plug in n equals 0, I get 1, and I get a 4th, then I get a 16th, then I get a 64th. Those are going to 0. Okay, so the terms are going to 0, so I can skip number 2. The terms are approaching 0. Are some of the terms in the series negative? Nope, move to the next one. Does the series involve factorials or exponentials? It does have exponentials in it, yeah. So this suggests that we could try the ratio test. And some series with exponential expressions may be easier to handle by thinking about a geometric series. In fact, did we skip over geometric series? Oh, yeah. P series, use the P series test or the geometric series test. Well, it's not a P series, but it is geometric. My constant multiplier in the first one is 3/4. X equals 3/4. And then the other one is x equals 1/4, which tells us that this converges, right? The geometric series test says that if that multiplier If that multiplier is between -1 and 1, the series converges. All right. Next sum, we want to notice that this is similar to a p-series when n is very large. So what p-series is this similar to? If you plugged in like a billion, the only terms that would matter would be the leading terms. And n squared over n cubed reduces to 1 over n. So we would compare to the sum of 1 over n here. We could use the direct comparison test or the limit comparison test. Yes. The coefficients don't matter when you're choosing a sum to compare to. Yeah, and because you could always, if I put a 3 over 7 here, you could always pull the 3 over 7 out. And then the 1 over n diverges whether you multiply it by 3/7 or not. Correct, yeah. Yeah. If the leading terms had the same degree, you know it would converge to the ratio of the leading coefficients. The terms would converge to, not the sum. Okay, so for this one, you want to notice the factorials and the exponentials, right? So if you check through our list here, there's a note about, does the series involve factorials or exponential expressions? Yes, so try the ratio test. Okay, so for D, we want to notice that this series alternates. So let's look at our list here. There is a question that says, are some terms in the series negative? If the terms alternate between positive and negative, we can use the alternating series test. We could also determine by using the absolute convergence test. Look at the absolute value. So there's two tests we could use here. Alternating series test or absolute convergence test. The details of how to use them are on the first page of your packet. So we're just trying to discuss which test might apply. Okay, determine whether the series is absolutely convergent, conditionally convergent, or divergent. So if we want to know if it's absolutely convergent, we have to look at the absolute value of all the terms. So for absolute convergence, I look at the absolute value of the terms. Just put absolute value bars around each term. And then -1 to the n. N's always going to be an integer, 1, then 2, then 3, then 4, right? So -1 to the n will always be +1 or -1. So when you take its absolute value, it is 1. So this is 1 over n to the 1/2. And 1 over n to the 1/2, we want to decide, does it converge or diverge? So let's look at our list here. Start at the top. Is it a p-series? Yes. So we would use the p-series test to determine if this converges or diverges. P is smaller than 1, so this diverges. Okay, so if I know that the sum of the absolute value of all the terms diverges, what does that tell me about absolutely convergent, conditionally convergent, divergent? Anything yet? Is it absolutely convergent? No. The absolute value doesn't converge. It's not absolutely convergent. So we can start there. Not absolutely convergent. So now I want to determine, is it conditionally convergent, right? It's not absolutely convergent, we've determined. Is it conditionally convergent? So now I'm going to look at the sum without the absolute values. If that converges, then we call it conditionally convergent. So my original sum, -1 to the n over n to the 1/2. The signs alternate. So if I look at my flow chart here, is it a p series? No. Do the terms approach anything other than 0? No, they approach 0. Are some terms in the series negative? So we use the alternating series test. To see that this converges. So the terms go to 0, the terms are decreasing and going to 0 and alternating, so it converges. So we would call this the original sum converges, but its absolute value does not, so this is conditionally convergent. Okay, 1 over n times the sine of n squared. So what I would want you to notice here is that the sine of n squared is always trapped between 0 and 1. So this is similar to a p series. It's 1 over n times a number, basically. That number is changing, but it's trapped. So I want to compare to 1 over n. And I could either use direct comparison or limit comparison. I think direct comparison is a little easier in this case. So what we would be doing for direct is you would look at the given fraction and compare it to 1 over n. Because the sine of n squared is always between 0 and 1, it's a fraction, right? Like, say, a half or a third. If you take a number and you multiply it by a half or a third or a fourth, does it get bigger or smaller? Smaller. So this denominator on the left is smaller than the denominator on the right. Smaller denominator, larger value fraction. So this fraction is bigger than this fraction. We know that this sum diverges, so this one has to also, because it's larger than something infinite. So I'm skipping the details on all these, but just because we're working big picture, right? Like, what test do you go to? Okay, just a couple more here. The sum of n squared over n squared plus 1. This is where the leading coefficients thing matters, right? So if I look at the limit as n goes to infinity of the terms, n squared over n squared plus 1, the degree of the numerator and the denominator are the same, so this limit is the ratio of the leading coefficients, which means the terms don't go to 0. So do the terms of the series approach 0? No. They approach 1. Which means that this has to diverge by the test for divergence. Right? So we'll look at quick check through our list. Do the terms approach anything other than 0? Yes, they approach 1. If they do not approach 0, the series diverges. Test for divergence. Okay, ne to the negative n squared. So this is really hard to do a comparison. So what I would do here is notice that the terms form a continuous decreasing function that can easily be integrated using U substitution. So if you look at f of x equals xe to the negative x squared, that is decreasing and positive and integratable. So we would use the integral test. The integral test is sort of your test of last resort, right? We're going to look through, is it a p-series? Nope. Do the terms approach anything other than 0? Nope. Are some terms in the series negative? Nope. Does the series involve factorials or exponentials? Not exactly, no. Is the series similar to a p-series or a geometric series? No. Have none of the above approaches worked? This is where you might try the integral test. If you could integrate without too much pain, try the integral test. So it works in this case because you can use U substitution. Yeah.
Why doesn't it have forces?
Yeah, it does involve an exponential expression, so you could try the ratio test. Yeah, there isn't a wrong answer here. Just tests that don't tell you much, right, or are too hard, right? So you could try the ratio test, but it might be that simplifying the fractions just gets too ugly because it's an exponential squared. Right? All right, so that's it for the demo. Your group activities for today and your homework for tonight is from the 5th edition, number 28 through 47, skipping number 45. From the Chapter 9 review, the problems are all printed down here. So we want to determine which of the series converge. On your first pass through, just use the flowchart and decide on what tests might be appropriate. Test or tests. Then make a second pass through where you work out the details of your chosen test. You have the solutions, not just the answers, but the entire solutions all written out on the next couple of pages. A couple of them use the integral test where it's unnecessary. I think it's number 30. So they use the integral test, but then at the end here, they say you also could have used the limit comparison test, which is like way easier. So if you see them using the integral test, like read to the bottom and see if they recommend something else. I think it happens again in 42. They unnecessarily use the integral test. Yeah. And then at the very end, they say you could also use the limit comparison test, and it's way easier.